Let's look at another example using inequalities and doing a proof. So this proof says if x and y are positive, then x is less than y if and only if x squared is less than y squared. So first thing that jumps out here is we have an if and only if statement. And if you recall from any previous proofs you've done, if and only if means we have to prove both ways. So we need to prove that if x is less than y, then that implies x squared is less than y squared. So that's the first thing we have to prove. And the second thing we have to prove is the other direction. So we have to prove if x squared is less than y squared, this implies that x is less than y. So if and only if proofs, we have to prove both ways. So we'll start working with, I'll label these 1 and 2. So we'll start with 1 first. So we're going to write our proof. So we're assuming this is true, and we want to show that we can get this. Okay, so assume x is less than y. And again, x and y are real numbers. And we need to deduce that x squared is less than y squared. Well, what we can do is use the third rule, and I didn't write them here. I'm hoping that you can kind of recall them. The third rule is we can multiply both sides of an inequality by a non-negative, or I guess I should say a positive real number, and we won't have to flip the inequality sign. So assume x is less than y by axiom 3. And if you can't recall the axioms, go back to the last lecture. They're on the they're at the top of that video. So by axiom 3, we can multiply both sides by x. And why x? Well, I have x is less than y, and I want x squared is less than y squared, so I'm just going to multiply both sides by x, and that'll get my x squared in there. So if I take, I multiply both sides by x on both sides, we can get x squared is less than xy. On top of that, we can do the same thing, but instead of multiplying both sides by x, we can multiply both sides by y. So we can say also, not actually write it just below, keep it flowing pretty nicely. Also, and again, we can do this because x and y are positive. That's our assumption's way up here. So that's why we can use rule 3 or axiom 3. So also, we can multiply both sides by y. So if I do that, again, I have x is less than y. And this time, I'll multiply both sides by y. And what I get is I get xy is less than y squared. Now, at this point, we can see that we can chain these together. So I can take this fact that we have. I can also take this fact that we have and put them together. Now, so I'll just write it explicitly. So with this information, we have, so we know that x squared is less than xy with the first yellow box. And we also know with the second yellow box that xy is less than y squared. So I kind of have my like first chain right here. And then I can do my second chain right here. And kind of group them together because I know xy is less than y squared. So I have x squared is less than y, or sorry, I have x squared is less than xy, which is less than y squared. If you recall by axiom 1, we had this rule, 5a real number b, and c is bigger than b, and a is less than b, then that means a is less than c. And again, if you don't recall those axioms, go back to the previous video and look at those. So what we can say is, move this down just a little bit. So therefore, by axiom 1, we have x squared must be less than y squared. And that is the first proof done. We still need to prove the other way. And so I'll just get rid of this as well, just using that for an example. So just to reiterate the first proof, we have, so I'll just move this up a little bit. We know that x and y are positive numbers. And we're trying to prove the first case right here, because we have an if and only if statement. We assume x is less than y, and we want to get this as our outcome. So okay, we assume x is less than y, and we multiply both sides by x. And we get this. Great. We also note that, well, let's just do it again, but with y. So again, we assume x is less than y, multiply both sides by y, and we also get this. So we have two things that are true. We have two true inequalities. And the big thing we can note here is these both have a common term, so I can link them together. So what I have is xy is kind of the mediator here. So I have this fact that x squared is less than xy, so I put it here. And I also know the fact that xy is less than y squared, so I put that here. Chaining them together by axiom 1 tells us that x squared is strictly less than y squared, which is what we wanted. So that's the first part of the proof. The second part, what we can do as well. So I'll put it kind of over here a little bit. So I'll move just a bit over. So I'll say like proof for 2. So this time we're assuming that x squared is less than y squared. This is what we're going to start out with, and we want to deduce that x is less than y. So let's do that. So we're going to assume x squared is less than y squared. Okay. What we can do is we can add negative x squared to both sides. So again, this would be axiom 2. So we'll say add negative x squared to both sides. And again, since x is a real number, negative x squared is also a real number. So what we'll do is we have x squared is less than y squared, and we're going to add negative x squared on both sides. It's a little too dark. I'll make that a little bit brighter so we can see it. And what we get is we get 0 is less than y squared minus x squared. So at this point, we can factor. So we can write this as a difference of squares. So you can say that we should write out what we're doing, right? So we can say factoring this result yields, and we can just say that y squared minus x squared, that's the same thing as y plus x, y minus x. And what I'm going to do is just kind of like flip these signs. So I'm going to write the y plus x and y minus x first. And we saw that 0 was less than that value. Another way you can look at it is, right, the alligator's eating the y squared minus x squared, so it's still going to be eating that term. Just a better way to look at it, in my opinion. Doesn't matter which way you do it. And that's not an axiom or anything, that's just rewriting how it looks. Okay, so we know that y minus or y plus x times y minus x is positive. So since we know that x plus y is positive, its inverse is also positive. Recall in the last video, we proved example 1.5. So recall if we have a value, we called it a, is bigger than 0, its inverse is also bigger than 0. That was the proof in the last video. So we're going to use this idea. So since, right, we could say x plus y or y plus x, it doesn't matter, right? So by example 1.5, since y plus x is positive, then its inverse is also positive. Now, how do I know that y plus x is positive? Well, remember, we know x and y are positive numbers. The sum of two positive numbers will be positive. So we can confidently say that y plus x is positive, which then in turn lets us know that this is also positive. So why do we care? Well, we can multiply this on through the inequality on both sides. So we have So I'll say so multiply both sides by the inverse y plus x to the -1. And the reason we do this is because it will cancel out one of these terms. And what we'll get is we have y plus x, right? This is just what we had earlier, not changing anything. So that's what we have. If we multiply both sides by the inverse, what we get is some nice cancellation. The inverse times something, or times its original cancels, and we're left with y minus x, and then 0 times anything will be 0. So we're going to be left with y minus x is greater than 0. And again, this is by axiom 3. We're multiplying both sides by a positive. I should move this over a little bit. We're multiplying both sides by a positive value. And by axiom 2, so I can say axiom 3. And then by axiom 2, I can add add x to both sides. I'll actually do it in blue, just again so we see what we're doing. And we get, and this is by axiom 2, we get y is greater than x. And what we wanted was x is less than y. So it is correct, but we can put it in that form. Y being greater than x is the same thing as x is less than y. So we can just say x less than y. Right, we see that the alligator is eating the y. The alligator's still eating the y here. So they're eating the same thing. And that is the end of the entire proof. So what we have, we assumed that x squared is less than y squared, and we got x is less than y. So we'll reiterate this proof. So we added negative x squared to both sides by axiom 2. Right, this is by axiom 2. Because negative x squared is just a real number, so we're allowed to do that. And we get a difference of squares, which we can factor. And we decided to take one of those factors and multiply both sides by its inverse. And we're allowed to do that because y plus x is positive. We can't do it by y minus x rigorously because we don't know if y minus x would be positive or not. The only information we're given is that x and y are positive numbers. But, right, we don't know which order they're in. So if we had, like, if y was 3 and x was 12, well, 3 minus 12 would be -9, so we wouldn't be able to multiply both sides by it without flipping it, but I think it's just easier to look at axiom 3 and just, we know for sure for any value that this will be positive, so we don't have to worry about any sign flippage. So what we do is we take the inverse of this, which is also positive by our example 1.5 in the last video, and we multiply both sides by that quantity, and we see that these cancel out because they're inverses, and obviously 0 times anything is 0, and we just get a simple inequality. We add x to both sides, and we get our final solution, x is less than y, and that's what we wanted. So this proof was a little bit longer because we had to prove both ways because we had the if and only if statement. So since we proved this, now we can use this in the future. So we know for a fact that if x and y are positive real numbers, if x is less than y, or I guess we should say, since we proved the if and only if, x is less than y if and only if x squared is less than y squared. So we can use both ways. So that concludes this proof. The next video will be another proof.